Title of his talk, but he's going to talk about the program a little bit and then give his talk.
Yeah, so we had a boot camp, but not all of you were here for this, so I wanted to talk about one aspect of the program that didn't quite get covered during the boot camp. So if you want to have a Simons program, you need to write a proposal, like a 10-page proposal, something like an NSF proposal. And then Simons has a scientific advisory board of like 15 leading researchers who you go and they ask you questions about your proposal. And they were quite perplexed, or some of the committee was quite perplexed about our proposal. The first question we got was, like, your proposal didn't mention what the big open problem in your area was. Like, what's the big open problem in your area? So I want to sort of say something about what the purpose of the program is by explaining like why they were confused. What were they expecting? So I'm going to talk about some research areas. I'm going to pick some old ones to not defend anybody, but there's a lot of optimization problems that end up, applications where there's an optimization problem that's some standard, NP hard optimization problem, but because of, on the graph, but because of the nature of the application, the graph has some special property. It's an interval graph or something like this. So David Johnson noticed this and, try to sort of organize research in this area. And in its NP completeness column, he produced the following table where the y-axis is special types of graphs, and the x-axis is NP hard optimization problems. And for each entry, he stated what was known in terms of being NP or being NP complete. So this was sort of this became a research area, complexity of NP optimization problems and special types of graphs. Here's another research area. There was algorithmic research on resource management, and Jan Carl Lenstra and others sort of tried to bring some organization to this problem, or to these types of problems. So they introduced this alpha beta scheduling notation to sort of be able to sort of essentially a three-dimensional table to sort of describe a problem that falls within this area. So this is an example of such a problem, and the size of this table is much too big to explicitly show you, but there's a whole website where you can enter alpha, beta, and gamma, and it'll tell you what's known for that table entry. So a lot of research areas, a lot of NSF proposals you get is there's conceptually a table of open problems in the area that's recognized, and what's proposed for the research is, here are the entries in the table that I'm going to sort of solve and fill in. And then, I guess what's expected in the Simons proposal is, you should identify the table entry where this is the big one, okay? So for example, scheduling, this table entry is the big open problem in scheduling, okay? Good. All right. But what is the consequence of this table is you get a lot of research that is, the starting point is there's an empty entry in this table. I'm going to fill it in. And the justification is this table entry is empty. Okay? And both Jan Carl Lenstra and David expressed some regrets that they sort of enabled this sort of research that was sort of divorced of the applications. Okay, there's some negative consequences to having such a table. All right, so let me just digress and tell you one other story. So around 2009, I was part of organizing a visioning workshop for NSF about what the science of power management as a research area might look like. So NSF was considering having a special program on science of power management. In order to do that, they need to write a proposal. In order to write a proposal, what this looked like, they need some ideas for academia. So the idea was to bring in a bunch of systems researchers, a bunch of theory algorithms researchers, have them sit for a couple days in a Hyatt, and develop some vision of what this area might look like. Okay, and my experience is that like a lot of the algorithms researchers just didn't get whatsoever what the goal was. I mean, they did not understand what this visioning process was. That I went around to these small groups and they were expecting somebody to tell them, tell me an algorithmic problem, I'll give you an algorithm for it. That was sort of what they were looking for. So part of this program is, yes, we're going to try to develop algorithms to manage emerging technologies, but it's sort of broader than that, right? It's trying to bring together people who are interested in what I call the sort of slow algorithm sort of research, right? Where you're starting from the application, not from this conceptual open problem, not from this table, okay? So, we had some talks at the boot camp where somehow the story was, we spent a year figuring out what the right algorithmic question was, and then we solved it at a dog stool. Okay, so it's sort of, more research in that sort of vein, and just sort of appreciating, trying to, have a greater appreciation in the algorithms community for that, that type of research. All right, so that was my spiel. Now I'm going to switch to my specific talk on racetrack or domain wall memory, not phase change memory, as on the web page. So good. So here was the starting point for my research on racetrack memory. I'll try to use racetrack memory and domain wall memory mean the same thing. I'll try to stick to racetrack memory because I think that's becoming a little more common. But here's Science 2008. Here's a table of various memory technologies. And it was a multi-dimensional table, but, to the left is good because it means it's a smaller size. Low is good because, it means it's fast. Small circles are good because it means it doesn't use a lot of energy. Green is good, means idle power is low. So down here, the bottom left, racetrack memory had the best of all the worlds. This was at least according to the Science article. All right. So, one question you might ask is is racetrack memory still a thing? Okay. Yes?
Just make sure I understood that graph. DWM was racetrack?
Yes, this domain wall memory down here. Okay. Sorry, they use both terms interchangeably in the literature, and all right. Yeah, so it's the same cost to read and write, but it's variable how much cost that is, and I'll get to that in a second. All right. But the point is, it was promising. This was somehow the takeaway from this. There's still academic conferences on, racetrack memory, so academics are still, still doing it. But one of the things that we learned in the boot camp is why aren't new memory technologies, that common that they're commercially successful? The two reasons that I heard during the boot camp was a lot of them you need some intelligent control, some management from the get-go, which is good for us. I mean, this is the sort of thing that algorithms do. So, this was what motivated my research. There's some interesting algorithm questions here to address. But the big one is economic. There's nothing we can do about that. Probably you should bet against every memory technology making commercially just because, it's so hard from an economic point of view, but all right. So, sometime after this, there was this program at NSF called Algorithms in the Field, which was targeted to, collaborative research between algorithms and applications researchers. So this seemed like a perfect fit. So I applied to the Algorithms in the Field program, and I got funding. So now, in the recent SIGAC news, maybe not the most recent one before, Peter Brass, who is stepping down as a program director for the algorithms program at NSF, had some reflections on his experience. And one of the things he said was that the AITF program was quite disappointing, and it wasn't renewed. All right. So I'm partially responsible for that. So one of the things that
Pointing out, there wasn't a good interaction between the application person and the algorithm person?
Rahul, do you want to? This is what I got out of Peter's article, so I don't know.
I think I agree with Peter in some sense. Yeah, it was my favorite program, but just as I go, the program goes away. So,
I'm a little surprised
I
at
like it,
the
I mean,
timing
I
of this. The program had already not been renewed before Peter got to NSF.
Okay.
I mean, it had transitioned to the logic in the field, which I forget what it's correct.
Formal method.
Formal methods, excuse me, in the field. And was he really talking about the algorithm in the field?
This is a direct quote from his article.
Because
It was slightly shortened, but I don't think this is.
Tracy claimed at the time that it was not renewed was that he wasn't getting enough proposals, which is, you could say, a measure of not successful, but I wouldn't put the blame on you for not having delivered what you proposed,
Okay.
but rather on the question of how much the community came together and generated proposals.
All right. I think I give part of the blame. The community, I will let you discuss how much of the community was to blame, but I did not contribute to the success of this, and I sort of want. So one of the things that Martin said during his talk, if you haven't had a chance to see Martin's talk during the boot camp, it's worth saying it's really good, is that you should see, this contribution is hard, and a lot of times it fails. So you should see, students and postdocs should be examples of both successes and failures. This is something that's less, mine was something that was less than complete success. Okay? All right. Up to where we go here. All right, back. All right. So, the first thing we have to do is go and figure out what domain wall memory is, what racetrack memory is, and if you go look up at the YouTube videos, there's a lot of physics, right? It's a little overwhelming when they talk about all the, the charge at each year, but conceptually, after a while, you figure out, look, it's just a tape. It's a Turing machine tape. Okay? That's what it is. Now, it's very small. It's small, right? These things are, this thing's a very small, is 1 to 10 micron levels, or at least at the time I did this. So it's very small, but in terms of and there's bits stored on here that are stored magnetically, and there's like a barrier, a wall here between these bits to stop them from influencing each other. And to read, you have a read-write head, and to read the bits, you put in some electrical current, and it forces some bit over the read-write head, and you read it. But this is a tape, right? At least at an abstract level.
What's the length of the tape?
I don't know. I've been out of this for a while, on the order of hundreds of bits at the time, but I think if it's going to be commercially successful, it would be, and have to be longer. Okay, so, all right, I will get to that in 2 slides. So one of the things is that if you see here, the access time's not a fixed amount, but it can go up or down. What's the explanation for this? If the next bit you want to read is near you, conceptually on the tape, then it's small. If it's on the other side of the tape, then it's bigger. Okay, that's why this line is variable here. All right, and the other thing that's different than is that it's not like one tape that stores all the bits. There's lots and lots of little tapes. Okay. I don't know. I'm not. Okay. I'm an algorithms guy. Once they told me it was tape, it was fine, and this was also many years ago. So I don't know.
Is the access time then linear in distance? Because it looks like there's a linear.
So I presume a good model is linear in distance plus some constant overhead.
Okay.
That would be probably a pretty good guess. If you go to YouTube, there's a lab at MPI in Germany that's working on this, and there's all sorts, you can go the first 15 minutes and they'll tell you number after number that doesn't mean anything to me, but if you can get something out of it, go for it. All right, so, what did my proposal say we would do? Well, sort of 3 levels. One, we'd organize data on one of these tapes. Now, since there's a lot of tapes, the second level was, okay, we'd organize lots of different data over lots of different tapes. And the third thing was, okay, now that we have that, we'll figure out how to put it in a memory hierarchy. All right? But we never made it past the first one. So we really just ended up figuring out how to manage data on a particular tape. All right. So kind of here is sort of the natural model, of what we're doing. You have something that's like a Turing machine tape. You have a sequence of memory accesses, and you want to you put the data there so that it minimizes how long it takes, the whole total tape movement, to access all of these things. All right. So what problem in a standard algorithms book does this remind you of? No, not case server. What's that? Move to the front. Yeah, this list update problem, right? So this is in Cliff's book, and it goes back to this very influential CACM article by Daniel Slater and Bob Tarjan, and there. What was the difference for them? This linear thing was not a physical tape. It was a singly linked list. Okay. But what difference does that make? So let me just show you an example. But they want to organize this singly linked list so the access time is small. What is the standard algorithm in the CACM paper or now in Cliff's book? Is you just, whenever you access an item, you move it to the front. So if I'm accessing E, I move to the right until I get E. Then I swap E left forward until it's at the front. Right? So I move recently accessed items toward the front. So conceptually, items that are accessed recently are going to end up toward the front of the list. And you can prove then that if you do this, your access time is within a constant factor of whatever the optimal would have been, if you sort of knew everything that was going to happen in the future and could optimally arrange things. All right. So now, what was different for us? What's different if it's a tape than a singly linked list? There's no reason why your read-write head has to come back to the beginning. Right? There's no reason. Okay, so it's exactly the same as the standard list update problem, but the tape head doesn't have to come back to the front. So if you guys were an undergraduate class, I would now force you to tell me some reasonable candidate algorithms. So I'm going to try this, and can anyone give me a reasonable candidate algorithm riffing off of move to front? Yes?
Previously ended that?
Yeah, or you pay to move it.
Okay.
All right. So I suspect you're just all too shy. So I think all right. So I think these are the natural ones. When you access something, move it next to the last thing you accessed, or move the last thing you accessed next to the next thing you accessed, or make the last two things you access, move them halfway in between. I think these are the 3 natural ones. None of these things work. They all are just as bad as you could possibly imagine. There's at least in the worst case, there's input sequences where, like, you're going halfway across the tape on every single access, and that was not necessary. All right.
So you're trying to capture locality of reference by moving the things close together.
Yes.
Right? Of course, you destroy, depending on how you move them, you may destroy other localities of reference you just created, right? At least the second one, for example, right? I think.
Yeah, to a large extent, we just found it confusing. Like, none of these 3 things work, but obviously you should have things you access together should be together, right? All right. And so so our takeaway intuition was it's harder because, like, you want to put things that are accessed near each other together, but it's not clear where you should put them on the tape. I mean, you could have a different takeaway, but this was kind of ours. So the most interesting result that I thought we found is that actually this problem is, there is no constant competitive algorithm for this problem. Like this seems, like going in, we were pretty sure this can't be that much harder than list update, okay? But it turns out that it is significantly harder, right? Which was pretty surprising to us. I like problems where like everybody's intuition, all the algorithms guys' intuition's wrong, right? And this was one of those. I also like when I go to a talk and hear a good homework problem. So if you're teaching algorithms and want a good Yow's technique problem that's doable, like a problem, a lot of these are too complicated. This one's sort of doable as a homework problem. So let me just sort of give you the idea. This is like the only thing I'll even try to prove. Yes, go for it.
So, I mean, one question that's sort of coming to mind in the face of such impossibility results is that one thinks about how constrained the memory resource is, one wonders about keeping multiple copies of the same item so as to improve access somehow. And is this a direction that people have thought about? Is it, from a practical point of view, completely unreasonable to think about it?
I think I'm telling you pretty much the totality of what I know, at least anyway. So to jump ahead just a little bit, so we're like, what's the right thing you should do given this result next? You should try to do probably either change the model like this or do some sort of beyond worst case analysis of some type and try to figure it out based on this lower bound what the right type is. That would be the standard thing, yes?
If you know ahead of time that you're accessing memory sequentially, like a row of a matrix or something, could you take advantage of that?
Yeah, so this would like be a beyond worst case approach. Assume you know something about your memory access, and then if it, like you had a prediction or something that it's going to be sequential, and then if it is, you should do well, and if it's not, maybe you shouldn't do terribly or something like this. All right, so this is sort of the idea that the right thing to do is you just have some fixed permutation of the items, and the adversary is just sitting there the whole time, right? And kind of what the online algorithm has to do is hide it, and what you do is you have like n log n accesses to all of these items. So like log n times you go through the items, but in different orders. Right? And each time you sort of are revealing more and more of the tree. So you start out, it's a random permutation of the items. And then at the second level, there's this tree sitting over here. And you kind of, you can kind of tell the online algorithm that, okay, like those two are together, those two are together, those two are together, those two together, and then you randomly permute these subtrees. Okay? So kind of, what you should just take from here is the input distribution is relatively straightforward. All right, and then if you think about it a little bit, on each iteration as you go through this, what information is revealed to the online algorithms, it knows what the various subtrees are, but at this level you might know that these are the 4 subtrees, but it has no way of knowing that C and D are siblings. Or A and B are siblings. It just as likely could be that B and C are siblings, or an A and D are siblings from the online algorithm's point of view. So it doesn't know how to organize the memory. Okay? All right. All right, what did we do after this? We did not what I said we should do. We did offline approximation because we're offline approximators and this is what we do. This took a lot of time, and this was just a mistake. Probably what we should have done is just said, like, organizing one tape where you don't have a home head is hard, and just assume you have a home head and moved on to organizing multiple tapes. Or come up with some beyond worst case analysis for one tape, but that's not what we ended up doing. So let me, based on this and just sort of my experience, what are some reasons why, maybe AITF was less successful than one might have hoped? And again, this is riffing off of some of the things that came up in the boot camp, Like you need a team of an algorithms researchers that's interested in this sort of research, a systems researchers that's sort of interested in, principle design, that sort of thing. And you need, a good PhD student who is interested in this sort of research. And like getting this team together at the right time, I think is challenging a lot of times. And it's, more challenging at some institutions than others. And another issue that we had is that this is sort of slow algorithms. It takes time. This is a 3-year grant. 1 year after I get funding, I'm now 1 year away from having to write my next grant. Right? So it's just we just didn't have time to get up and get things going before, I need to be thinking about what am I going to write as my next proposal. So I think, those are somehow the reasons, in addition to whatever my shortcomings in doing the research, these are some reasons why we were not more successful.
What happened to the systems researcher who presumably was on the proposal with you?
This is being recorded.
Okay. I didn't ask who it was.
We did not have all of these components, ideally situated. All right, so one of the things that we're going to do, I think the plan is next week, is we're going to try to sort of, riffing off what we heard this week, can we as a group of long-term visitors and fellows come up with some interesting algorithmic questions related to memory management? Okay, and we'll sort of work on those. Here are some, so if you're giving a talk this week and you have some suggestions, what might be interesting algorithmic problems for people to work on the next couple of weeks that aren't like on your critical path or something, like, it'd be nice if somebody invested this aspect, feel free to mention those. One is, if you sort of home the read-write head in the middle of the tape, there's a trivial 4 competitive algorithm riffing off a move to front. Can you do something better? Don't know that that's, the most interesting problem in the world, but it's might be a reasonable startup problem. How can you manage multiple tapes? Like again, maybe you want to sort of do move to front on multiple tapes, but if all the popular items are on one tape, what can you do? Can you do something interesting? Any sort of beyond worst case analysis. All right, here is, how am I doing that time? Okay, all right, so I'm good. So here's one problem. I'm still sort of interested in this list update without a home. So here's a problem that's easier than that problem. So I just have a bunch of integers. This is sort of my ground set. And at any point in time, I have to color my numbers. Every number has to be colored red or blue. Also, roughly you need an equal number of red or blue. I forgot to add that restriction. You can't color everything blue. And then over time, just pairs of integers arrive. If those integers are colored different colors, you pay 1. Otherwise, you pay 0. And you can always recolor things at a cost of 1. Right? Minimize your cost. This is somehow strictly an easier problem than this list update sort of version without a home rewrite head. And I don't know how to do this problem, and it seems hard. All right, that's it.
Questions?
Continuing on the pathway of bad here. So you mentioned the lower bound. Is there an upper bound for randomized?
We can do a super complicated polylog offline approximation.
But nothing is known online. Right?
Online is, I don't even think square root of n. I don't know that I tried square root of n very hard, but I don't know how to do square root of n.
Do you get to read all the things in between when you're moving the head from one to the other? Can you just read all the things in between for free?
Yeah, I would think so. I don't know. And I would think as you move, you can swap them as you're moving. That all seems reasonable to me. Modulo.
don't think you said it, but do you know what's happened commercially with racetrack memory?
Yeah, this was my slide where there's still academic conferences going on. There's still research. I mean, I don't know. I'm a little skeptical commercially. I mean, I think there's been some physically built, but I don't know that you can commercially buy it.
You mentioned this deterministic for competitive when the home
Yeah.
is in the middle. Randomized for that setting?
So what I really like is just something that's simple. Like, yeah, I mean, you certainly could do better than 4 if you use the better than 2 randomized.
Better than 2, yeah.
Repeat the question.
Oh, the question was, can we do better than 4 randomized? Sure. I mean, the thing is, anything you can do where the read-write head's on the left, you can do when it's at the middle time still. So you need to, can you do something better than that? So again, if like all the popular things are on to the left of the read-write head, then presumably you should balance them. Yeah.
So, I just want to kind of zoom out a little bit. Like, if you're going to be reorganizing the locations of the data, then you have to have another table somewhere telling you that, right? So you can't be doing this on the granularity of bits, because then your metadata is larger than the data, right? So what exactly was the vision for closing that gap?
We did not have a vision.
Okay.
I mean, we did not. I mean, I think the thing is, like, if you can't, I mean, imagine you magically had a solution for that problem. We still have problems. So, maybe the takeaway is, it's not even worth thinking about that because.
I mean, you can just chunk it. You can
Yeah.
say, we're gonna chunk it into 128-bit or 250, whatever, and then move them to chunks.
I mean, I think at the highest level, the takeaway is if you want to organize data on a tape, locality of reference is much harder to maintain than you might first think, given that you've read Cliff's book or something like this. Like, it's not, your intuition might take you in the wrong direction.
I was just going to speak a little bit in favor of these algorithms in the field program.
I think I touched the nerve on this.
Someone who thinks had a successful, grant funded by it. I thought it was great. I was really sorry when they ended. And I think what he said about not getting enough proposals may be true. But I don't know, for me it was great, and I tend to think it was successful.
Yeah, but I think one of the reasons they didn't get a lot of proposals, it was tough to get a team together. I mean, this is challenging.
As someone with a rejected proposal, I think that they inflicted it on themselves.
So, just for those of you who don't know, so how NSF evaluates whether a program was successful or not? So I was there for ITR when they evaluated ITR. You call in all the people who got funded and ask them whether it was a good program. I'm sure they do other evaluations, but my takeaway from the ITR funding one was everybody that got funded thought it was a great program.
As again, I liked all the proposals, including him, including yours. And I like all the proposals in IITF.
Thank you. Next, we'll have Stephanie Miller speaking.